Hi, in this video, I will be showing you problem number 33 of chapter 14, section 7. Find the absolute maximum and minimum values of f on the set D. F of xy equal to x square plus y square plus x square y plus 4. D is all those xy's such that absolute x is less than or equal to 1 and absolute value of y is also less than or equal to 1. So we'll underline the keywords. Absolute max and absolute minimum are what we are going to find out. The previous problem was about local maximum and local minimum, where we did the D test or the second derivative test. Here we have to use the extreme value theorem. So how do we find the values that the extreme value theorem guarantees? Find the values of f at the critical numbers of f in D. It's kind of similar to the idea that you guys did in Calculus 1 class single variable. And find the values of f on the boundary of the domain D. Then the largest of the values from the steps, above steps, is the absolute maximum value. The smallest of these values is the absolute minimum value. So first, to find out the critical points. Second is to find out the extreme values of f on the boundary. So this is what going to be a bit computational process because of the nature of the domain D. The domain D is in this case a square. So it's absolute x less than or equal to 1, absolute y less than or equal to 1. This means that x lies between -1 and +1, and y lies between -1 and +1, which is a square. So depending on the boundary of D, this step can take a bit of time. It is computational. The largest of these values from the above steps is the absolute maximum value. The smallest of these is the absolute minimum value. So let's graph the domain, which is a square. Absolute x less than or equal to 1 and absolute y less than or equal to 1 mean that -1 less than or equal to x less than or equal to 1 and -1 less than or equal to y less than or equal to 1. So we'll draw the square. The -1 +1 for x, -1 +1 for y, and we'll complete the square. And then we will mark the boundaries, which are the edges of this square. Mark the endpoints, which is -1, -1, and 1, -1, 1, 1, -1, 1. We'll call the boundaries as L1, L2, L3, L4. L1 is the boundary with y equal to -1. L2 is the boundary x equal to 1. L3 is the boundary y equal to 1. L4 is the boundary vertical line x equal to -1. So we've graphed. The second step is to find the critical numbers, critical points. So it's obtained by setting first partial derivative of fx to 0 and fy to 0. Fx is 2x plus 2xy, partial derivative of f with respect to x. Then partial derivative of f with respect to y would be 2y plus x square. Setting fx equal to 0, we get 2x times 1 plus y equal to 0. This would give us x equal to 0 and y equal to -1. We'll plug both of these into fy equal to 0. That gives us 2y plus x square equal to 0. So if you plug in x equal to 0, which is from here, into this, and we get y equal to 0, substituting x equal to 0 into fy equal to 0, we get y equal to 0, and substituting y equal to -1, Substituting y equal to negative 1 into fy equal to 0, we get negative 2 plus x square equal to 0, which would mean x square equal to 2, which would mean x equal to plus or minus square root of 2, but square root of 2 is 1.414, which exceeds 1. So we know that absolute x should be less than or equal to 1 according to the domain description. So we have to disregard this, which is not inside the domain, the one x equal to plus or minus square root of 2. So the only critical number is going to be just 0, 0. Both values lie inside, both values don't lie inside the domain. So x equal to 0, y equal to 0 is the only critical number inside D. The next, find the value of f at the critical number, at the critical point, namely 0, 0. Just f at 0, 0. So f at 0, 0 equal to, if you plug it into the original function of f, you get 0 square plus 0 square plus 0 square plus 4 equal to 4. So f of 0, 0 equal to 4. Then we have to do the boundaries, L1, L2, L3, L4. Then what are the maximum values and minimum values at these boundary values? Then we have to pick the largest of all of these as absolute maximum. Smallest of all of this will be the absolute minimum. So the boundary values are what we are going to find out now. What is happening on the boundaries? So find the values of f on the boundaries of the domain D, namely on the 4 sites L1, L2, L3, L4. So we'll do one at a time. On L1, what is something fixed? Y equal to negative 1. That is fixed. X can be anything. So f of x comma negative 1, if you plug it into the original function of xy, f of xy, you get x square plus negative 1 square plus x squared times negative 1 plus 4, which will be just 5. So f of x negative 1 equal to 5, which is a constant. Now what happens on L2? On L2, x equal to 1 is fixed. So we get f of 1 comma y. If you plug it into the original, you get 1 square plus y square plus 1 square times y plus 4, which is equal to y square plus y plus 5, which is a quadratic, and if you graph it, it's going to be an open upward parabola, which is an open upward parabola. Keep in mind this is the nature of the function on the boundary L2. So f of 1 comma y, which is y square plus y plus 5, if you complete the square and find out the standard form, it is y plus 1/2 the whole square plus 19 over 4. So this is a parabola with vertex at negative 1/2, y equal to negative 1/2. So open upward parabola will have a minimum at the vertex corresponding to negative 1/2, but the maximum is attained on this when y equal to 1, on this L2. Right? On L2, this quadratic in y, namely f of 1y, attains the maximum at f of 1, 1, at 1, 1, and the maximum value is f of 1, 1. So if you plug this into the original function of f of xy, you get that value to be equal to 7. So keep track of these values as we do. Then where is the minimum occurring? Minimum, as I said earlier, it's going to be happening at the vertex corresponding to y equal to -1/2, but x doesn't change on L2. It is still x equal to 1. So is attained at the vertex for y or at 1 -1/2. So if we use that, f of the minimum is occurring at 1 -1/2, and the minimum value is f of 1 -1/2, which is 19/4. So we got on L2 what the maximum is, what the minimum is. L3 corresponds to y equal to 1. X can be anything. So f of x comma 1, if you plug it into the original, you get x square plus 1 plus x square, which is plus 4, which is 2x square plus 5, which is an open upward parabola again. Attains its max at 1, at -1, 1, and at 1, 1, because it's second degree. So at -1 and +1 on that line L3, when y equal to 1, both at -1 and +1 for x will yield the maximum value. So f of plus or minus -1, or you can write f of -1, 1 and f of 1 comma 1 both are equal to 7 by plugging in -1 square here or +1 square here, get this to be equal to 7. What about the minimum? The parabola 2x square plus 5 equal to 2 times x minus 0 square plus 5. So it's an open upward parabola. The vertex corresponds to x equal to 0. That's where the minimum is attained. Y doesn't change on L3. It is still 1. So the minimum is attained at 0, 1 on that line. So it's an open upward parabola with vertex corresponding to x equal to 0, which is the minimum value, minimum point. But on the line L3, y is fixed. So the minimum at 0, 1 would be f of 0, 1, which from the original equation is 5. So we got information on L3, where the maximum is, where the minimum is, what those values are. Then we have to do L4. What is unique about it? X equal to -1, that is fixed. Then y changes. So f of -1 comma y. So if you write that and plug it into the original, you get y square plus y plus 5, which is, as we discussed earlier, which is an open upward parabola. The maximum occurs at -1, 1. The maximum value is f of -1, 1. If you plug it in here, you're going to get that value to be equal to 7. The maximum is -7 and it occurs at -1, 1. So where does the minimum occur? Minimum will occur corresponding to the y value for the vertex of the parabola. So x doesn't change, it's still -1. Similar to the previous discussion, y square plus y plus 5, using completing square, we get y plus half the whole square plus 19/4. And with vertex corresponding to the value -1/2, which corresponds to the minimum. On L4, the minimum occurs at the point -1, -1/2, and the minimum value is f of -1, -1/2, which is equal to 19/4. So we got all the information on L1, L2, L3, L4, which are the boundaries of D. Now we have to make a conclusion, and we have to decide which one is the maximum, which one is the minimum. So what have we found so far? So f at the critical number is equal to f at the critical point is 0, 0. F at 0, 0 is 4. This is one information. Then on the boundaries, on L1, this is what we found. F x comma negative 1 equal to 5, which is a constant, does not change. On L2, the function is f of 1 comma 1 will be the maximum value, which is 7, and the minimum value is occurring at 1 negative 1, which is f of 1 negative 1, negative 1 half is the minimum value, which is equal to 19 over 4. On L2, the maximum value is 7 and the minimum value is 19 over 4. The maximum occurs at 1, 1. The minimum occurs at 1 negative 1 half. Then on L3, the maximum value is f of plus or minus 1 comma 1, which is equal to 7, and the minimum value is f of 0, 1, which is equal to 5. On L4, the maximum value is f of negative 1, 1, which is equal to 7, and the minimum value is f of negative 1, negative 1 half, which is equal to 19 over 4. So we got all these values, and biggest of all of these is the absolute maximum. Conclusion is the absolute maximum is the maximum in all the parts that we got in summary. The absolute maximum is attained at plus 1, 1 and at negative 1, 1, with f of plus or minus 1, 1 being equal to 7. That is the absolute maximum value. And the absolute minimum value is attained at 0, 0, and the absolute minimum value is f of 0, 0, which is equal to 4. Okay. So getting absolute maximum and absolute minimum will involve certain amount of work, some amount of work. So the whole thing is that you find out the critical point and you find out the shape of the domain, and then discuss the maximum and minimum values on the boundaries, and then including the critical point and including and together with the maximum minimum values on the boundaries, whichever is the largest is absolute maximum, whichever is the smallest will be the absolute minimum. We'll do one more problem based on local max, local min in the next problem. Hope this video helps.